Okay, good morning, everybody. Welcome to Friday, day 5, final day, final plenary. Today is the project Keynote plenary. Every year, at least like for the past couple of years, the project plenary Keynote has celebrated some aspect of Rubin that has sort of come to completeness. So we've celebrated EPO a couple of years ago. I think last year we celebrated the completion of the camera. And this year we are celebrating survey strategy. So you're going to hear from 3 people today about sort of the road to survey cadence optimization, a bit about the history, why it was put together as a community effort, and about all the inputs from the community that have come in along the way. So you'll hear from Phil Marshall, Lynne Jones, and Federica Bianco today. But first, we're just going to start with our usual reminders that there's a code of conduct and 3 people who are serving as code of conduct contacts. If you witnessed or experienced any violations of the code of conduct, contact them anytime, even next week and in the weeks after the meeting. As always, wear a mask if you want to, and keep an eye on those social battery pins. A reminder to our virtual participants to please stay muted and use the Slack space to ask questions. And when you do, let us know if you want them spoken out or if you'd prefer to unmute, and we'll arrange that for you. Just 2 announcements today. One is that there is an exit survey. You can find it at ls.sd/Y8P. Please do the exit survey. We look at every response, we put them all together, and then we make changes for next year. And it's really useful and really informative. So take a moment to do that exit survey today or in the week to come after you're home. If you're going to the airport today, there's a Slack channel, RCW-Carpool, where we will coordinate sharing rides to the various airports. And that's it. I'm going to pass it over to Phil.
Thanks, Melissa. All right, let's see if I can operate 2 handheld things at the same time. Okay, so as Melissa said, celebrating something that is completed. Unfortunately, well, fortunately for us, survey strategy is not completed. You'll hear over the next hour just how not completed it is, but at least the road towards it is paved. So we thought we'd spend some time telling you a little bit of the story of how this all came to be, because we've learned some interesting things along the way about not only the Rubin system, but also ourselves. Okay, so I thought I'd start with this. You've probably seen this on the YouTube. It's been up there for a couple of years now. But I was reminded of it when we were doing the virtual tour earlier in the week. Look how fast this thing moves. Yes. So when I was in the dome and marveling at the Simone telescope, Chuck Claver was there reminding me, or telling me for the first time actually, that the reason we're not allowed in the dome at night is because it moves so fast. And at the time, the telescope was pointing at the horizon, and he just pointed out that if the telescope were to start moving at survey speed, I wouldn't be able to outrun it. So now, of course, we have a very fast telescope and also a very big camera. You've seen these pictures this year of the LSST camera first being completed, then shipped to the summit, which was fantastic to see. And so we now have this almost complete system on the mountaintop, ready to start surveying at high speed. And thinking about this talk, I was figuring that probably all of us in this room have had some version of the same experience over the last 10 or 20 years, which is a realization of what it means for Rubin Observatory to be so fast at surveying that you end up being able to take so many images over such a long survey period that you end up with a data set that really can be used for a very wide range of science, a synoptic survey. And then I remembered, oh yes, the telescope used to be called the LSST. And so I went back digging out through history to see where we got started with the survey strategy. It turns out that the overview paper, which you've all read and know and love, that derivation of the survey, what we were planning to do, sort of first appeared in the science book in 2009, or T-16 as we now know it. And so I went looking in here to see, well, where were we at thinking about survey strategy back when we were writing the science book, and pulled out some text to admire. There's a bit in the beginning of the science book where we go through the science requirements for the survey. But the bits that I really like in this nice paragraph is just the pointing out of the survey being truly synoptic and what that means. It means making a single data set to serve most science programs. And there's a clue in here about how the survey strategy could then evolve over the next number of years, which is that if you take away one of the science drivers, I don't know why you would ever do that, but if you did do that, it wouldn't really change much of the requirements for the other three. So there's some robustness to the survey coming from the design of the system from its beginnings. And then also look at this little sentence at the end, the conclusion of the people writing the science book, that this was a survey for everyone. And that sort of got us in the right frame of mind, I think, for thinking about the survey strategy in more detail. Here's an early figure of what we imagine the survey strategy might look like, made with an early version of the operations simulator tool, which shortly after 2009, everybody just called OpSim forever. But it was nice to see that even back as far along ago as that, we were already underway with a vigorous and systematic research effort. It's good to see. So that was our starting point. So over the few years after that, as this research program got underway, we started to think, well, what about doing as best we can with this system? That we have a starting point survey, but how are we going to optimize that to do the best we can with science? So here's a slide that I made in 2014. I was talking to a group of strong lensing people and telling them a bit about what I thought we were going to need to do. And there was this thought at the time that maybe the tools that we were building, the operation simulator, and also this thing called MAF, the metrics analysis framework, were getting to the point where they could be given out to the whole community. And I remember overhearing Dave Monet start to worry about the possibility of the cadence wars that might ensue if we were to give the community this power to imagine surveys that would serve their science to the detriment of all others. And so at that point, we were predicting that, yeah, there's going to be a lot of work on observing strategy coming up. But this cadence wars statement got me a little worried, because in a war, everybody loses. Some people lose everything, of course, but every individual loses something. I think that's probably self-evident whenever you see anything like it. And maybe most importantly, in a war, it's really a whole lot of people working together to actively lose their togetherness. So fortunately, we didn't do that. Here's a couple of years ago. Here's how together we are. Look, we turn up every year for these community workshops, and we put on the T-shirt that is handed to us. And here we are as a team. And hopefully it's felt to you this week that this is a team all working together towards a very broad set of science goals, but at least with a deep appreciation of those science goals. Okay, so we started a program of cadence diplomacy instead. That was around 2016. And here's the talk I gave at the PCM, interestingly, it was called in 2016 in Tucson. And you know the rules of extreme programming, right? Code should only exist in one place. So I'm not going to remake the slides that I showed then, but here they are. We knew that the science depended on the observing strategy. We were already aware that we needed to care about uniformity for cosmology. That was a starting point. We had other examples of things we knew we needed to worry about. And this was the baseline survey strategy at the end. This is the 10-year depth plot. You can see somewhat similar to where we were a couple of years before, but we were starting to think, well, how should we change this? How can we go beyond the baseline? And we knew that we wanted that process to be science-driven. There needed to be some way of hearing from the science community about how the survey strategy was going to work for their science. And so the idea was to really lean on this metric analysis framework, which you're going to hear a lot more about in a second. The metrics that we're talking about, the ones that we knew then would turn out to matter most, are these figures of merit, things that somehow summarize how well the survey strategy of Rubin will work for your science case, written in such a way that they can be put alongside everyone else's metrics and compared. We also knew back then that we were going to need to work together. This is the diplomacy aspect of it. We decided that we should really do this as a community, and we could benefit from figuring out how to make this math code work together. But we could also try and identify the tensions and trade-offs early so that we could work through them together. And so we decided, okay, we'll write a paper together. That's what scientists always do when there's a collaboration to be done. And so this is the white paper that came out of this first effort to work together on optimizing the survey strategy. 85 people worked on this. It was a big effort at the time, and a big commitment of people to spend their research time thinking about a survey that was still in the somewhat distant future. A remarkable thing. Okay, so there's the story so far on the left. The tools were built in 2014. Then we did the COSEP, this community white paper. Here are the two boiled down outcomes from that. The Science Advisory Committee reviewed the COSEP, and they recommended that the Rubin project implement and analyze this rolling cadence idea that had come up. But also look at this one. Go ahead and execute a systematic effort to further improve the LSST cadence. So that led to a whole lot more of this kind of thinking. So after that, there was a sequence of things like the white paper, but reimagined every couple of years and presented differently. So instead of one white paper, the next thing was to collect 46 community white papers. Amazing that people wrote so many. That led to a change in the baseline strategy. That was followed a couple of years later in 2021 by 39 more papers, this time called Community Cadence Notes. This steady and large stream of information coming into Rubin about what the observing strategy should be. You'll notice that at some point in there, 2019, Rubin stood up a special committee to look at this, the SCOC. You'll hear more about that in a second as well. Okay, so since T-10, we've been counting down to the survey and evaluating and iterating the survey strategy at every step of the way. Look how many people have been involved in this effort. It's an amazing community effort to get to this point. And you can see just briefly here some of the changes that happened to that 10-year depth map over the course of this process. Okay, so this took a lot of work already by hundreds of dedicated people working with some very good tools, and we thought it'd be worth spending a bit of time telling you a bit more of that. You can see this nice paper that Fed led for a more detailed history. But right now, you're going to hear a bit from Lynne Jones, who will tell us the story of the math and how it supports survey strategy decision making. And then after that, you'll hear from Federica, who will say more about the Survey Cadence Optimization Committee and all the work that it's doing at the moment. So Lynne, over to you.
Yeah, thanks, Phil. That was great. I always love how diplomatic Phil is, and like the whole cadence diplomacy idea is very much, I think, something that you've helped forward. Okay, so I'm going to talk a little bit about how we sort of set up all of that science-driven balancing of the survey strategy goals. And in the process, I had to dig out a lot of things that were from way, way back. And I also found a presentation that I had given a long time ago. So this is a slide from a presentation I made to the PST back in 2014 when we were first standing up the metrics analysis framework. And it was kind of about like, hey, why do we even need this and what does that look like? So very early on, when OpSim was first being developed and we were looking at the simulations of the survey pointings, there was a lot of one-off analysis to kind of address performance questions that were mostly related to system engineering. So one of the things that is not maybe so well known is that OpSim very early on answered some very fundamental questions about the project, such as what should the field of view actually be for the telescope in order to be able to cover the sky at the rate that it needed? And also, how many filters should be in the filter changer? So we have 5 instead of 4 because of early OpSim analysis like that. That one-off kind of simulation evaluation evolved into what was known as the S-STAR report. And this was sort of a 40 to 60 page PDF that was generated for each OpSim run that was made. Again, it was primarily like based on either static science evaluation, and it was a per field analysis. It was very sort of custom, like this is this thing, let me calculate it. And the idea was we wanted to be able to get to merit function prototypes, which were cadence-oriented metrics, and make that easy to run. So that is what we had coming into why we would build the metrics analysis framework. But what we needed was something that was more flexible for new metrics, something that could handle dithering, because the old OpSim outputs did not have dithering, and the old analysis was not very good at handling dithering. And something that could let us engage the community in evaluating simulations by letting them focus on metrics instead of pulling visits out of OpSim and figuring out where visits were pointing over the sky, things like that. So as an example of the kinds of thing we were hoping for, this plot shows on the left side is co-added depth as it was simulated by those early OpSim pointings where they were fixed field pointings, there was no dithering. And then what happens when you add dithering? So I think these were some of the very earliest analyses we did with the prototype of math way, way back, and looking at things like what does the power spectrum of the M5 depth look like? So our goal was to create an easily extensible, that is, anybody could write a new metric, customizable, you could run any subset of metrics in ways you wanted, open source, so that it was easier to accept contributions, Python framework for evaluating simulated survey pointings. And today, MAF does contain hundreds of metrics with a wide range of complexity. So I'm going to sort of quickly blast through plots of a couple different kinds of metrics that we have, just to it's a very small subset, but I just wanted to sort of illustrate some of the range. And if you see your metric up there, thank you very much. These ones are metrics that are coming from sort of system performance. So these are, we do and always have tried to measure the system performance relative to the SRD. So very basic things like the number of epochs over the sky, proper motion. We also look at metadata, like how close are we getting to the moon? What's the distribution of sky brightness, the distribution of the timing of visits. But when we try to optimize the survey cadence for science, we have to also look at DESC, static science and transient science, solar system science, transient and variable star science, Milky Way static and transient science, strong lensing science, AGN science, galaxy science. And all of these metrics have come through a combination of contributions from the project, but also a lot of contributions from the community. So in order to get to that point of being able to have all those metrics from the community, we did need to go through a process of supporting the community to work with math. And in the early days, this looked like workshops at every PCW or all hands meeting. I think the first one we had for math was in 2014. In 2015, there was the Cambridge Cadence workshop. And I think this was the first purely cadence math focused workshop that there was. And it's very memorable for me because due to a variety of reasons, I had to take my then 2-year-old daughter with me. And I had to bring in all my family from Wales to help look after her. And it was an interesting trip, but it was great. We have put on a lot of talks and short workshops in science collaboration sprints and hackathons. Then, of course, there was the 2018 LSST Cadence Hackathon, which was supported by Heising Simmons and LSST Discovery Alliance, sorry, which was then LSSTC. So thank you very much for that support. This was an amazing hackathon that brought together people across all different science collaborations. And we sat down and we had a lot of work on math and a lot of work on just talking about what the cadence should look like. And a lot of the ideas about how do we bring all of this together and make it work for everybody came from this workshop. In fact, there was a white paper that came out of this that was I think at the time called Big Sky Diplomacy, and that was from Keynote over there and Co. And that was a really, I think a lot of our footprint that we have now for the survey is like owes a lot to the footprint that came out of that white paper. We've also done yearly workshops. As the SCOC got stood up, this is sort of an SCOC sponsored workshop. They organize it. We have tutorial repositories. We've done on and off virtual office hours, mostly on during the time of lead up to things like the cadence notes. And we've done a lot of support via email, Slack, and community.lsst.org. And I will say, the nature of that support has changed over the years. Not only is the community now, in general, often much more math knowledgeable, and plus we have all those resources like the tutorials out there already. We are not starting from scratch, as well as the community is not starting from scratch. But also, think back to what you knew about Python or Git in 2014 or 2013. And think about what you know today and how your attitudes towards that have changed, or how the attitudes of your students have changed about that. And we're working in a very different environment now than we were then. So I did want to go through a list of some things we learned then or now in preparing for this workshop. I don't think any of these are all that new to anybody who's actually done a lot of work on software where there's also people contributing and you're trying to do tutorials. But we all learn these over and over again, right? So documentation is hard and it gets outdated. But saving and clearly dating your presentations and documentation is worthwhile for reference, for both for other people then and for you later when you're like, wait, when was this? We did this thing? Okay, right, okay. Having a stable API for your package and well-defined API is important, but sometimes you do have to break things. People having access to lots of data is great. People like that a lot, but sometimes you do have to do, but they probably won't look at it all. And so you have to do some work to figure out how to narrow it down for them. And that's hard so that they can see what they want. We have a lot of metrics, right? We have these hundreds and thousands of metrics, and making it so that people can see the things that they need to see has been a challenge. And it's been a significant source of the work that I've had to do to figure out what makes sense to look at and what do other people want to look at. This is sort of a reflection now. And remember, again, I said like people's sophistication in Python has definitely increased over the years. People's comfort with other people looking at their code has increased over the years. But more effort at the point of accepting a pull request in GitHub in terms of cleaning up code while you still have the authors, they're still available, would probably have been worthwhile for our code base. Adding unit tests for people or making it much, much easier to add unit tests would have been a worthwhile thing for us to do as well. How easy it is to access your software and data is really important. When we made math the very first time, we were in the LSST software environment and it was EOPS installable. That became a little bit easier and then a little bit harder. And it was possible, but it was a significant stumbling block in trying to support people to use math. Eventually we made it Conda installable, and that was a vast improvement. A lot more people installed math at that point. we still had some stumbling blocks, and we had this huge increase in users. But when MAF and a series of OpSims became available at Noir Lab, on the Data Lab, and on SciServer, the number of people writing metrics increased by an order of magnitude. And so thank you very much to Noir Lab, Data Lab, and to the science collaboration members who got MAF up and running on SciServer. That was really helpful and really important. Nowadays, you don't have to worry about it because the RSP is now available. So we did get a lot of community contributions to MAF. First, that was to the repository we had at the time, which was Sims Math, and also Sims Math Contrib, which is where most of the community put their contributions. And now these are all in RubinSim. And that our code has benefited immeasurably from the contributions from the wider group of Rubin LSST project members, but also the community members outside the project. And so thank you again for all of your work. As I said on Wednesday, we're not done, of course, but thank you. It's great. And I think that MAF probably contains the most direct from the community Python code in all of Rubin. And these are being contributed via like pull requests on GitHub, co-working where like we've sat down with somebody and we've been working through a metric, developing it with them, and then maybe we do the pull requests and commits. Contributed notebooks where maybe somebody has sent us a Jupyter notebook and we've pulled the pieces of code out of that and put it into MAF. So the plots here are from what you can actually get from GitHub, but they don't represent all of the contributions we've had and all of the contributors that have contributed to RubinSim, because it's hard to track the people who didn't go do that through GitHub. But on the bottom left, we have the contributions to Sims Math Contrib. So this is almost entirely external contributors from the community. And you can see that reaches all the way back to 2014. It goes all the way up to 2021, which is about when we closed that, we stopped using that repository and folded things into RubinSim, which continues over here. So RubinSim includes project contributions too, so it's a little bit less fair to compare them directly, but that length of time of contributions is, I think, very impressive. And I did make a grid of all of our contributors who contributed via pull requests or commits that got into those repositories on GitHub. So if you see yourself there, thank you. If you don't see yourself there, but you did send us code, thank you also. All right, so our goal was an easily extensible, so we could get metrics from the community. You see, we did that. Customizable, we do actually run some metrics and not others. Open source Python framework for evaluating simulated survey pointings. And MAF has provided us a way to incorporate a wide variety of these metrics. We can run all or some of them for a given simulation, and we can immediately see the effects on the survey strategy on many, many science cases. So yes, I think we built a useful tool. I think it was working out. What is the future of MAF? All of this work is not for nothing. We're not done using this. Metrics will be part of the nightly, weekly, and quarterly reports on survey progress. I've pulled a little snapshot from one of our prototype nightly reports. So this just shows you the nightly coverage over the sky, what happened last night and how that builds on what's been previous. The plots here look a little bit different than the ones you're used to seeing, but this is just a slightly different representation. And this is built in on MAF. Metrics will continue to guide survey strategy. So Phil said, we're not done and there's still more to do, but also it would be incredibly, I don't know if I would say disappointing or boring, but like the survey strategy will continue to change during operations. As we find new things, there'll be science reasons to change the survey strategy. So yeah, we're not done with survey strategy. And one of my team members, Eric Nielsen, said he was changing the DES survey strategy up until the very last days. So there you go. And metrics, we will continue to use them to predict survey performance at the end of the survey. I will also point out the ConsDB in operations is like the OpSim output database, but live and for real visits. And so you could think about, like, can I make a metric that's going to alert me to a science case that I would like to go and investigate more deeply? Okay, I did want to just talk really briefly about the evolution of the scheduler, because the scheduler has also evolved. So Phil showed this plot from a very early version of OpSim. What's incredible to me looking back at this is that we had a single baseline survey from 2009 to 2016, which is a really long time compared to how fast we are updating those now. The old OpSim took several days to run. It didn't have any dithers. It had a very limited flexibility in how you could change how the survey strategy was presented. So most of our simulations are now based on, well, all of our simulations now, and most of the simulations over the history of this work is based on the feature-based scheduler. The feature-based scheduler is more flexible. If you can think of a way you want to survey this guy and turn it into a Python code, we can probably do that. It's more flexible. It runs faster. So now it's about 8 hours for a full 10-year simulation. Dithers are included when you take the observation, and we can investigate far more options in the survey strategy. Also, this is the brain of the scheduler in operation. So this is the piece of code that picks out what should the next pointing be. You can also see up at the top there that the pace of outputting simulations really picked up, and also the number. So now we have the SCOC who are looking at all of these options, and we have more variations that we want to investigate to understand what's the best survey strategy we can do. We have many, many more simulations that we're running through. The future of the feature-based scheduler. So Oxtel is currently almost 100% driven by the scheduler. I would say using the feature-based scheduler, I would say 100%, but there are very rare occasions where they do something else. Commissioning will use the feature-based scheduler among other options for scheduling those observations. And when operations start, the feature-based scheduler will be choosing observations for the LSST. So we will also continue to use the feature-based scheduler in simulations so that we can continue to do things like evaluating the survey strategy for various strategy options. Also, we use it to simulate what will happen in the upcoming night, the upcoming year, or all the way to the end of the survey. Okay, and I just wanted to close out by putting up some information about the survey scheduling team. I really appreciate my team members. It's me, Peter Yoakum at University of Washington. He's been through all of this work, like setting up the MAF, setting up the FBS, handling all the early morning meetings, whenever, and Eric Nielsen, who is joining our team now for operations, and he's now working on a lot of the survey monitoring and reporting tools, which I think are going to be really useful and interesting to everybody here. All right, and Fed. Oh, won't give it away.
Hello, my name is Federica Bianco. I'm Deputy Project Scientist for Rubin, and my primary responsibility in that role is to lead the Survey Cadence Optimization Committee. So some of the things you've heard from Phil and Lynne, you heard that Rubin early on had this inspiration that if we really wanted to be a survey for everyone, then everyone had to help us figuring out how the survey should be run and optimizing the choices that we were able to make within the system to really get the best science and the most science. And then you heard from Lynne that Rubin has invested effort, time, and support in making sure that people could interact with their system, could interact with their simulations to guide us in the decisions on how to optimize the survey with software, and actually a lot of time, of people's time, to support the use of that software. And we did talk about cadence diplomacy instead of cadence war. And certainly this is where we're going for. But there are choices that have to be made. One can envision the system of Rubin with like a very high level. The choices that you would make are, do you want to have a fast cadence, or do you want to repeat observations in the same position rapidly so that you can do transient, even fast transient science? Or do you want to have a regular and persistent cadence and follow things for the whole 10 years of the survey? Do you want to go deep, or do you want to go wide on the sky? Do you want to get filters repeatedly at various changes so you can get colors? Or do you want to get observations in the same filter so you can get rate of change of brightness? And all of those things will be preferred by some science and disfavored by others. So this is just an illustrative plot of like 3 simple choices, but this dimension, the dimensions of this cube of choices is obviously much higher. And there's a lot more science than I could put in this slide. And the science lives in different places of this cube. And so we had to find the best compromise that really optimizes the survey. So we have the people that are contributing the insight. We have the system and we have the vision to do this, but we need somebody to be responsible for making decisions. And in 2020, the Survey Cadence Optimization Committee was instituted. The person that will make the decision, of course, is the director of the observatory. Hello, Bob. But the Survey Cadence Optimization Committee, or SCOC, is the body that will advise Bob in what is the best strategy that really maximizes science for Rubin throughout. And these are the heroes of this part of the story. There's about 10 to 15 people on the committee. The rotation is 2 years. You've seen several of the people here at the meeting, for example. You've seen Franz Bauer giving one of the presentations on behalf of the AGN Science Collaboration on the Science Collaboration Plenary on Wednesday. You've seen Louise Edwards giving one of the amazing science highlights at the plenary yesterday. And then there's Lynne and I. We serve on the committee we don't have a vote. I chair the committee and Lynne serves as ex officio. All right, so these people are incredible scientists, and primarily they're chosen for the scientific insight and expertise, trying to diversify the committee along many axes, including scientific competence, and had a really fun hour or so last night trying to pulling out visualizations from papers of the committee members, and I see all these beautiful plots that they authored with their scientist hat. But also, they serve as our liaison to the community. The committee is very public-facing. We have a lot of meetings. Lynne talked about the annual workshops that we run. We have office hours. We regularly present at meetings like this. And also the liaison, the SCOC members work as liaisons into the science collaborations. And you see here the matching based on scientific expertise and also participation in the science collaborations outside of the role of SCOC. And this is a bit of a delicate balance because these people are asked to be expert on a science, and to communicate with the science collaboration that likely do that kind of science, but also to be impartial and not to advocate for that science just because it's their science, so that we can truly arrive to the best science altogether for Rubin. So I feel like not only they're a very public-facing committee that have a really hard job, and they're also kind of in a tricky position. The work that we do on a day-to-day basis, we look at realizations of maths, of metrics, against simulations. Sometimes we look at them like this. This was a comparison of 2 baselines, one that introduced a throughput change that came with coding the decision to code the mirror, the 3 mirrors in the system with silver that increased the throughput in old bands rather than new band. And so we look at this circle in the center, which is our comparison, our starting point. And then we look at the new simulation baseline 3.3 in this case. And in this case, it's the orange lines. They're all outside of the blue. So that's great. That means we have an improvement overall in this set of metrics that we're analyzing. This visualization works for few metrics, but very often we have to look at a lot more metrics. So sometimes we look at metrics like this. These are metrics that are designed by one of the task forces of the SCOC. to improve the strategy on the Milky Way. So these are all Milky Way focused OpSims. And we look at different metrics and how the OpSim, the metrics respond to the OpSim. Up is good, down is bad. And we see, thankfully, that we have many metrics here that improve the science throughput of Milky Way science cases. We can fit a few more metrics here, but often we have to look at more metrics. This is another way in which we look at metrics. Here, blue is good and red is bad. And in this case, we have simulations that are stressing a specific parameter. These are simulations designed to test the filter balance. And so you see these blocks because we're changing things in the OpSim that are related in each of the blocks. We look at this plot, and of course, we also see numbers and quantifications, and we try to see what is the best compromise, what is the best choice that overall maximizes the science throughput of the survey. This is still a small set of metrics. Sometimes we look at a lot more metrics. I kid you not, I did take this from one of our notebooks. So we do look at things like this. So I hope that I'm conveying that it is a very hard job that the SCOC members are doing. Okay, our recommendations are conveyed in documents that we call reports, phase 1, phase 2, and in September you will see the phase 3 report. This report will be the last report before the start of LSST. But the SCOC is a standing committee of the observatory. So I want to iterate again that our work is not done. Our work is almost done to get us to how we will do the survey in the first year, how do we plan the survey starting from there. But we will be responsive to science changes and to changes of our understanding of the Rubin system so that we can continue to improve and change the survey strategy to continue to achieve better and better science. Okay, I'm gonna take you through some highlights and evolutions of the survey strategy under the work that we described and the SCOC in particular. So this is 2018, not very dissimilar from, what was it, Lynne, 2009? We had the first one of these plots. Some significant changes, in fact, already here, but look at what happens. In 2018 is when we received the white papers, the 46 documents written entirely by the community and delivered to Rubin. At the time, the SCOC was not formed. It was formed, in fact, as a consequence of the understanding of what it takes to review such a large body of work. 2021, these are the most obviously visual changes that I can show you. So these are just changes to the footprint. In particular, look at how the galactic plane footprint has changed. The galactic science in Rubin has evolved tremendously under the OpSims. The expectation for the science has improved massively over the course of this decade. More changes in 2022. And the survey, the baseline that we're gonna propose in September, at the moment, we think will look something more like this. Let me take you through some of the other highlights that you cannot just as easily visualize in these 10-year depth, 10-year number of visits maps. This was already mentioned. The introduction of the concept of a rolling strategy dates from roughly 2015. And the SCOC has endorsed this as the strategy that Rubin will follow. This means Rubin will observe the sky with high intensity area and low intensity area that will be exchanged, hence the word rolling, from year to year. So you look at a region at high intensity one year and low intensity the following year, so that you can get higher cadence and maximize transient science, the transient and variable sky, which is one of our core science pillars, but still maintain the sky depth and the sky and the area of the survey. We have introduced microsurveys. These are surveys that use very small fractions of the Rubin time. The one that you see here is the annual survey that is designed to capture objects in near Earth orbit, solar system objects. These are enhancing specific science goals and then can be done independently of the overall survey strategy. And they take about 1 to 2% of the Rubin time. We have finalized the location of the deep drilling fields, and we're still working on finalizing how we will observe them in detail. We finalized the final depth of the deep drilling fields, the dithering scheme, and a lot of other details about the deep drilling fields. And we've introduced, this is particularly dear to my science case, which is fast transients, we've introduced the concept of triplets. So Rubin will observe with 2 observations at roughly 33 minutes, median of 33 minutes separation. That gives you the ability to discover a moving object. But if you take them in different filters, you also get more or less instantaneous observations, all things considered. So you get a color for transients, which gives you a temperature. And then if you add a 3rd observation in one of the 2 filters, then you get a rate of change. So you know how things change in brightness and how their temperature is changing. And this is really crucial and important for transient science. So back when we started the survey, there would have been no way to detect or recognize kilonovae. And in fact, at that time, nobody was talking about kilonovae because it was pre-GW discoveries. But now we have the expectation to discover tens of supernovae serendipitously in the survey. So we talked about minimizing unhappiness. I think this word was coined, this concept was coined by Jelko. This is such a hard problem. It's gonna have to be a compromise. So we can only really aspire to work towards minimizing unhappiness. But I wanna show you here how really nearly all science cases that we're looking at in our metrics, nearly all of them have improved from the simple ideas that we had on how to run the survey in 2015. So I hope that you agree with me that certainly we're aspiring to, but I think we might be succeeding, in fact, at really maximizing happiness instead. So I did say the heroes of the story were, yes, of this part of the story were the SCOC members, but really overall, for the entire story, the hero is the community, and that is for sure. Just some snapshots of the hackathons and meetings and collaborative working session that we saw, that we discussed earlier. We went from having a few authors. I think in 2016, maybe the first conception of the concept had 25 contributors. And then the concept itself had over 100 in the end. In 2018, I counted 465 individual authors of the white papers. Now we're certainly over 600 people that have written white papers, cadence notes, or, as we'll see in a second, published peer review work that is guiding the choices of the SCOC and of the observatory. This diagram on the right shows the collaborative nature of this work. This is a plot of all the 46 papers, white papers delivered in 2018, colored by the science collaboration of the first author of the paper. And the links show like how many people were contributing to more than one paper. The largest one of these papers introduced the concept of target of opportunity observations, which is now endorsed by Rubin. The Rubin system wasn't designed to work as a follow-up machine, but then the gravitational wave discoveries happened, and they were so exciting that we had to adapt our survey strategy to this. That had 26 co-authors from across science collaborations and communities. And we were able to work with the IOP and AAS journals to set up a special issue dedicated to Rubin Survey Strategy optimization. This issue collects the work of the scientists that have written white papers and cadence notes. Those white papers and cadence notes were turned into peer reviewable material, and then turned into peer review papers so that people could get scientific credits for the work that they're doing. And I think it's really exciting that we already have a focus issue of Rubin, which at the moment count 21 open access paper contributions, and we're still at T-1. I don't think other surveys had that. Okay. That's all I had. And questions for any of us?
Yes, could you expand a bit on the changes for the optimization changes to the survey strategy to optimize the kilonova follow-up, or not follow-up, the serendipitous observation?
Yeah, we do have the program that will follow up kilonova will follow up gravitational wave triggers, and actually also solar system triggers and neutrino triggers, so multi-messenger astronomy more comprehensively. But the changes that we introduced to the survey strategy that allow us to have visibility into timescales that are intra-night or within a couple of nights, and those include the introduction of the rolling cadence, as well as the introduction of this triplet concept, where 1 out of 7 nights, a field gets a third observation in one of the 2 filters that it was observed with to begin. So you get visibility into timescales of hours and then few days, which would have been completely blind to if we just ran the survey without the triplets. So that Igor has done all the work on quantifying what is the improvement on this kind of science from this. And it's really significant. You multiply the number of kilonovas that you will see from like a couple to a few tens, right? Did I get the numbers right?
Thanks. So maybe I missed it. How much motion are we seeing on the telescope, from image to image? Are we talking like a couple degrees? Are we talking 20 degrees?
I'm sorry, I missed the first part of the question.
Sorry, I'm asking about, the physical aspect of the telescope.
Right.
How much motion between captured images are we
well, of course it varies, right? Because depending on where we're going, but most of the time, because we want to be as efficient as we can on the sky, we're going to just the next field over, which is a about 3.5 degree slew, right? And from the process of that slew, and then the telescope has to settle for a second before we open for the next visit, and it's about 5 seconds.
Yeah, okay, thanks. I didn't know if we were just going one field or if we were going farther than that. So.
Most of the time we do, and you can see it in the little simulation here that a lot of the time we go to the next field and then we'll move over to a different region. So there's a variety.
Oh, okay. Thank you. My question is mainly for Lynne. The math is such a complex but useful tool to everyone. So much effort went into it. I'm wondering if there is any plan to, or in your opinion, it's possible even to adapt it to other future telescopes, and specifically if there is any plan to use a similar system for Roman Space Telescope.
So Roman might be a little bit different because a lot of the way that Roman I'd have to think about. For other telescopes from the ground, it is actually totally possible. A very, very long time ago, in order to show that, hey, math might be useful for people doing things now, I ran a CFHT pointing history through it just to make a map. As long as you have the metadata about the pointing, you can take any set of visits and run your metric. So I know Eric Bellum was using it to have a look at some of the ZTF visits, for example. But yeah, I don't tend to show those examples, but it is fully possible.
This may be a question for Phil. Fed was emphasizing that the SCOC will continue throughout the survey and that there's an opportunity to adjust survey strategy as new opportunities arise and we understand the system better and so on. Can you describe a little bit more about how that decision process would happen? I assume it's the director's responsibility to make that decision, but it's a big enough decision that I imagine it will be a little bit fraught. And anyway, wanted to get your thoughts on that process.
Yeah. So I'll start, and then I might hand the mic to Bob to finish up. So yeah, high level, you have it right that the SCOC is advisory to the operations director, and it's important that it's a committee that looks at strategy, not tactics. And so the recommendations from the SCOC will give us the kind of the blueprint for designing that year's schedule. it is advisory and it is a blueprint, and there will need to be some tactical changes as well to cope with things that come up. And of course, some of those things that come up will be changes in strategy coming from the SCOC. I think what will happen when the SCOC submits its report and we get those recommendations, there will then need to be a lot of discussion and analysis within the operations team to understand the practical implications of what's being advised, and then we'll need to find a balance between what's possible, what's affordable, and what's being recommended for the optimization of the science. And that will need to get into the difficulty of the processing, the costs of making changes, that kind of thing. Bob, do you want to add anything to that?
I'll just second what Phil said, and I would just say, fundamentally, I would view going forward into the survey and looking at any needed changes or desired changes to the survey strategy is fundamentally building off the SCOC's work, continue to use them. And then, of course, as Phil said, as it gets time to make decisions, we would involve others, both in the observatory and in the community, to make decisions. I mean, this is the community survey.
One thing we will need to do, of course, is to circle back to the SCOC and explain why we can't do the things they're recommending. So there'll be a dialogue for sure between the operations team and the SCOC.
Yeah, there's one question from Zoom. Jiang-Hee, if you want to go ahead and unmute.
Okay. Thank you. I was involved in 2018 white paper. I'm very impressed how much it has evolved to TBS and many other things. But since recently I was not involved, not sure what it's important that this all our community effort to convert into the science paper. So I think I recommend make a Slack page with the science collaboration topics. So people in the, on the way, it's long years of effort of this, then, can get benefit of science. I'm not particularly talking about course, but I have idea to write the TBS and supernovae paper with the LSS data. Then I want to communicate with others, to not overlap with others. So that will be a good idea to, kind of way to give a reward to community.
Hi, thank you. Yeah, so my recommendation is there's many ways in which we are connected with the community. I'm going to briefly list them and make some recommendations specifically to you. I know you, so I think I might know what works for you, but listen to please all of them. So the SCOC does work very closely with the science collaborations. So if you're a member of a science collaboration, the best way to participate in this process is to reach out to your science collaboration to figure out what is the way in which internally they work on maps. Some science collaborations have task forces, some have working groups, some work more loosely, but there's always people that are working on maps in really all the science collaborations. The SCOC is also putting a lot of effort into being transparent. And that includes, we have a dedicated topic survey strategy on community. We update Lynne runs detailed updates of all the OpSims that get produced and shows the maths plots corresponding to these new OpSims. We post the minutes of every one of the meetings of the SCOC, which happen at least monthly. We post those minutes on the same community post. And there's a lot of contributions that are initiated from the community with questions on how to do things with map, or where are we with this particular parameter of the observing strategy at this time. So those are all ways in which you can interact with us. We also hold office hours on the last Monday of the month at 7 a.m. Pacific. And there is a new webpage that describes at high level the process and the current highlights of the OpSims and the maths, which Lynne maintains. And I don't remember the URL, but we'll post it on the Slack channel.
Thank you.
Survey.strategy.lsst.org. Oh, The LSST.io, that's right. I'm looking at the chairs of this to cut us off, okay? Maybe Tony's last question.
Yeah, thanks. Observational astronomers have this experience very often of being on a mountain looking in the morning as the sun is rising and seeing all the domes pointed west. And I noticed in this movie that that's also true here. And generally speaking, all these observations are a little bit weighted to the west. And I'm thinking that probably that is trying to finish up unfinished business.
So
to fields that aren't covered as well as they should have been.
So I don't think it's necessarily true of this simulation of 2.0, but that it's funny that you mentioned falling over to the side of the sky. That was definitely a problem with the very early OpSims and the simulations that we had. And the reason why is because the telescope slews faster in azimuth than in elevation. And also, if you go very far in elevation, you take a penalty in the slew time because you have to redo the closed optics loop. So the initial simulations were just considering one observation at the time, like what's the next best observation, and that's an algorithm that's very prone to falling over. The new feature-based scheduler doesn't do that in general. Towards the end of twilight, in like the last 15 minutes, we do sort of say, what's the next best observation one at a time? So you might be seeing that there. Also, it's not in this simulation, but in like newer baseline V3 simulations, we have this near sun twilight survey that operates in the twilights that actually tries to go very close to it's actually the other direction because it's trying to get towards the sun, right? We have been aware of this problem and we don't see it like as much in the new simulations. It's possible that there's still some slight effects there, especially towards the end of the night. But throughout the night, we're generally trying to get observations in pairs. And so, yeah, there is a little bit of an effect of like, oh, let's finish up this pair because we do a blob and then another blob. But on the whole, we don't tend to fall over with the telescope. So that's good.
Yeah, Melissa is telling us to get up, Bob.
All right. What a wonderful plenary. It's been an amazing week. A lot of great progress has been conveyed. A lot of great discussions have been had between the observatory folks and everyone else in the community. This venue has been tremendous. It's been a beautiful week. Interesting to have multiple sites on the same campus. I think that's worked out pretty well. I certainly have enjoyed it. I've enjoyed seeing all of you folks. We will be communicating the time and exact logistical details for next year's meeting, which will be back in Tucson. And it'll be in, around the same time of year. But it will be, I think, even more amazing than this because we will be right in the middle of it. We'll be right in the middle of some really exciting things. Oop, too fast. Just wanted to give you a quick view of this, of yourselves. This was our group photo for the week. Really nice to see everyone here and having such a great time. So, and we had lots of good participation online, of course, as well. So I want to take this opportunity. There's some folks over here. I'd like you to come out if you're here, or if you don't feel like it, you can stand there. But we tried to get everyone up here. Not everyone wants to come out or was able to, but in any case, there's a tremendous number of people who make a meeting like this a success. But it's not just this meeting, right? These folks who have put together this meeting, organized it, made sure everyone got where they needed to be, made this week so smooth and so technically effective for all of us. They're part of our community. They're part of our observatory. They're part of our institutions. And what they do is just as valuable as what we do. And because without them, we couldn't do what the science part of this endeavor. So it takes everyone to contribute and to make a meeting like this successful and to make a survey like LSST successful and to have gotten us this far. So thank you very much, you all and everyone that's here on this screen and even others who may not be listed here. But let's give them a huge round of applause. We absolutely value your contributions. You're part of this endeavor. And when those first images come out next year, you should all take as much pride in them as we do. Thank you. Okay, we're almost there. Just a couple more slides. This has been an amazing meeting. We're at T-1, and we're just every week or every month, you're gonna hear about great things. You're gonna tell us great things as we approach the big day. Just imagine as you get back, and you kind of relax after this meeting by thinking about, what's going to happen at the next community workshop. We'll have had first light and we'll have been celebrating it. The data preview 1 will be available and we'll be working hard with you and you with us to understand it and to get even more ready for what will come next. The start of the operations in the LSST will be imminent. We'll probably be right in the middle of it. So it's going to be a super exciting meeting. And then the other big message, which I think just fits so well with the plenary we had this morning, is that we're doing this together. Everyone together, everyone has a role to play. Everyone's contributions are valuable and make what we're doing even that much better. So we're all in it together. This next year we'll have challenges. It'll have excitement, maybe even a few setbacks here and there. But if we stick together, we'll get there together and we'll do the LSST and we'll start it soon. Thanks.